let X be a convex subset of Rn of a real number set. Ma'am, Rn is over here is the is a real number. No, is ma'am over here it's the dimension of a matrix, right?
Yeah, it is a real number only,
Or a real number set.
but having the order uh, number of elements, the cardinality n. Can you hear me?
Ma'am, why do they have to ma'am, but then why do they have to mention this every time? I mean, because in all the questions I mentioned this, and
Whenever,
sort of
whenever,
uh, we sort of skip through this
yeah, whenever we have a set,
while answering the question.
whenever we have a set and a relation, because you are talking about functions, and functions move from domain to range, domain to codomain. So it is important to tell that what is domain, what are the elements in the domain, which set they belong to, and what are the elements in codomain and which set they belong to. We can say natural numbers only. So here real numbers means you can take any example, uh, be it rational or irrational. So whenever you will see relation or function, you need to explain that what is the domain, what is the range from where it is moving to where, in which direction. So it is important to explain
Got
the
it, ma'am.
cardinality and order. Yeah. So
Ma'am, so they are saying let X be a convex subset of a real number with a cardinality n, where the function goes from domain to codomain.
mm,
Over here, domain is X and your codomain is the real number.
mm.
A convex function, a concave function, a convex subset, okay. Function moves from a concave function. Uh, G goes from again domain to codomain, but then codomain has a cardinality M, a convex function. A is a vector in the real number. Consider the following problem. Maximize A which belongs maximize X which belongs to capital X, and the function subject to Gx less than or equal to A. What is Lagrangian? What is the Lagrangian for this problem? Prove the Lagrangian is a concave function of the choice variable X on X.
So first of
Whoa.
all, it is a mix of convex concave concept and Lagrangian. And secondly, if you talk about this X convex subset, because domain is X, and you remember support theorem says that it is always open convex set which we take.
Open convex set. Yes.
So it is
Open
starting.
convex
It
set.
is
Yes.
nothing. It is nothing new. They are just introducing that we are taking up convex subset, and it is moving. There are two functions f and g. F is concave and G is convex.
Got it, ma'am.
Now you have to x, maximize fx, and this x value for f is from the domain set. And the condition which is given to you is this g, which is a convex function, is less than or equal to a, which is, of course, the condition of convexity, right?
Got it, ma'am. Ma'am, so over here, could we use a Lagrange?
They are saying that yes, what is the Lagrangian for this problem? So though we cannot come to exact x value, but we have to tell them the range. So how can you approach this?
So if it's Lagrange, the only thing that comes to my mind is fx plus Lagrange bracket A minus gx,
Correct. Perfect.
and you.
What we'll do, firstly, we'll write that whatever is given to us, that let x, here x is already
That's
given
not how
to
we
us.
do it, no, ma'am.
Yes. What is it saying? X is a convex set.
Yeah.
Then
Ma'am, what is the difference between a convex subset and an open convex set?
it is subset when we say that means it has been taken from a superset. For example, I have a set of a natural number x, and do you know set builder and roster form?
No, ma'am.
Okay, so basically, let's say I have it is that's okay. See, let's say I have a 2468. Tell me what is it? What do you think?
It's a set of all the even numbers,
Yeah, what is a
or
set?
multiples of two.
What is a set?
Collection of numbers, things.
Yes, well-defined objects. If I say best actor, list of best actors, is it a set?
Yes, ma'am.
It is not. Then,
Sorry, because it's well defined.
yeah, it is not well defined. The criteria of thinking varies from person to person for you. I mean, for this particular thing. But when I say natural number or even number or all the actors, then all the actors will come. If you introduce any adjective, be it good or bad, then it will not be a set. Okay.
Got
Now
it.
when I write set, I always use capitals, and these are elements and members. If I have to write this, every element belongs to. This is the symbol of belongs to the set. And if you want to make a subset, means the part of that set, then put that element in curly braces. That will become a subset.
Okay, ma'am. Just one second. I'll write this now.
Yeah.
Ma'am, so this becomes a subset of A, right? This A be a subset of small a.
Small a, subset of capital A. For instance, I have this. This is my main set. Then the subset will be elements are 1. Now here 2, 3 is not a set because this is given as an element here. In the
Yeah,
curly braces, whatever is there is an element. And 4. So all these belongs to. If I want to make them a subset, then I need to put them in curly braces. Are you getting my point?
got it, ma'am. Ma'am, so over here, when we so A belongs to capital A, the curly bracket A is just a way of representing A belongs to capital A, right?
Curly braces means it has the significance that now this is a set whose answer is A only. If you have 2, 4, 6, 8,
Hmm.
this is a set of even numbers. So 2 belongs to that set, 4 belongs to
Yeah.
that set. But now 2 is a set itself. It can be the answer for a set, let's say,
Oh,
even prime number.
got it, ma'am. I'll write this down.
Yeah.
Done, ma'am.
Then we have two things. One is how to represent a set And there are two forms, roster form and set builder form. So let's say I have written this. So this is exactly the number which I can see it is roster form. Now if I have to write set builder, that means I'll write an arbitrary number that this is X. This set will
Such that
contain,
X is all.
yes, such that this is also the sign of such that this is also the sign, colons or this pipe. X such that X is, tell me what is the similarity in all of them?
Ma'am, so it is all of it is multiplied by 2 of the previous number on the set.
So 2 raised to n.
2 raised to power n. Yeah.
Now because you are introducing n, you need to always define it. That n is a natural number. That means it is starting from 1. And I don't have upper limit because it is an infinite set. So I'll write the lower limit only. And then I'll write that n belongs to natural number set. As soon as you get this caps uppercase, then that means it is a set only. Are you getting my point? What is it?
Ma'am, as soon as n is, you got it.
So
Yes,
let's say
got it.
I'm writing this 2, 4, 6, 8, 10.
Got it,
I
ma'am.
can write it in the statement form that becomes the set builder. X
That
such
is
that
already a set. Yeah.
either X
That
is
is
an
set.
even natural number, or you can write X such that X is 2n and define what is n. Clear?
Yes, ma'am.
Now, when I say subset, because you have asked for it, my natural number is a superset from which it is taken. A set of even natural number is a subset. Okay? How many subsets can be there? This is the probability theorem, 2 raised to power m. Remember that if you are tossing 2 coins, how many
Yes, ma'am.
outcomes will be there? 2 raised to power 2, 4. Head, head,
Yeah.
head. So similarly, if you have, let's say, these are my elements. 2 elements are there. So this set will be having 2 raised to power 2. 4 elements, 4 subsets. So it is like the definition of composite numbers that, okay, the set itself and phi. Phi means empty set.
Okay.
Is the subset always, and remaining, just separate them. So these two are naturally the subsets. Subset means part of that set, that superset. And rest, it is like creating a sample space. Okay.
Got it. Ma'am, so over here there are 4 subsets, 2, 4, 2, 4, and 4, 2.
2, 4, 4, 4, 2, and
And
5.
empty set, sorry.
Yeah.
And an empty set. Ma'am, yeah, we retain the order.
Yes. Empty set, you know, right?
Yes, ma'am.
Okay. Let's come back to this bit. So why it is convex subset? Because you can see that X is just a part. Fx we are focusing on, and it has the values of X which belong to X. There will be a larger set, but X is the subpart. That's why we are calling it convex subset, okay?
Ma'am, so we have a larger superset. Let's just say the superset is A, and X. So over here, X curly bracket X belongs to A, and we have we have X which belongs to curly bracket X, is what they're saying.
Yes.
Okay.
So, now what we have to maximize fx for the value of x. And this
Hmm.
is the condition which is given to us. So we have been writing what is given to us. Why I can't?
Yes, ma'am. This is what we had written. This is
Huh.
what we had written.
F is x is a convex set. F is moving from x to r, which is a concave function given to us. G
Ma'am, X is
is
a convex set, and F moves from X F moves is large X to R, and G function moves from large X to R, but
yeah,
with a cardinality M.
Mn are the elements number that is not something which we have to consider, but we can see that okay, concave and convex thing is given. So what we are supposed to do, we have to optimize this using Lagrange. So you know that Lagrange means what? If you have, because only x is given, so we have Lagrange for x and lambda, right?
Yes, ma'am. Just X is given. Yep.
So what will be the expanded form of Lagrange?
Ma'am, so over here it's gonna be it is going to be Fx plus lambda gx minus a. No, a minus
Constant
gx.
first. Yes. Perfect. So
Constant.
this is my thing. Now I need to consider the members. How many members are there? Because those many values of lambda I'll be having, right? If
Yeah.
constraints are exceeding, then so as the Lagrange's multipliers, so I'll say that this lambda can be anything, let's say j, from 1 to m, anything.
Ma'am, no, I did not understand this.
Okay, so there are various values. If you, okay, you will write, let's say you are given gx less than or equal to a. So it is a minus gx. But there will be
Yeah.
n number of values for x from here
Yeah.
because it is g is from rm. So m number of values will be there, right?
Yeah.
So you have to expand for all of them. Lambda a minus g1, g2, g3, g4, g5, right?
Okay, ma'am. Ma'am, so I'll just write this down 1 second. This counts.
Yeah. So you
There
are
are
having,
m number plus b x comma lambda equals fx plus summation of j equals 1 to m lambda j. Hmm. Ma'am, I did not understand how what does this say? So this is summation of uh all the lambdas from where the all
let's say, here you
from 1 to
must be,
m.
am I audible?
Yes, ma'am.
So I'm saying, let's say this instead of this constraint, you have been given, um, let's say values of gx, various values of gx, that 2 is less than a, 2 plus x is less than a, 3 minus x is less than a, various values. So for this, what you must be having? Lambda 1, a minus 2.
Yes, ma'am.
For this one, lambda 2, a minus 2 minus x.
2 minus x.
For this one, lambda 3, a minus 3 plus x.
Oh, got it.
So
Ma'am,
if
so
I
since
have,
over here also we have
hmm,
multiple values of, oh, since the constraint over here is not just since the constraint here is not uh m-
it is not
ma'am, but
defined, only
ma'am,
the
but for
function is
example,
given. Huh, huh.
so let's just say if we take one of these constraints, so if we don't take two less than or equal to, if we take 2 plus x less than or equal to a, and if
Huh.
we say that, and if we say that, oh,
It is not because x can be anything. It is because g is defined from x to r raised to power m. And there are n number of elements for that set. So x can be combined with any one of them, make a function. For any value of x, there will be m values of r, right? See, x is domain, r raised to power m is codomain. So
hmm,
whatever gx will be, you will write x belongs to x. You will write small x belongs to capital X. That means you can take any value of x from this capital X. And so
hmm,
as you will be getting the final value from the codomain, and it is having m
yeah,
number of elements.
got it.
So this function will be having, this g will be having m number of ordered pairs, right?
Right.
So if there are
Ma'am,
m
so does
numbers,
any function, any constraint function you have mentioned. Even 2 plus x less than or equal to a will have multiple,
Lagrange multiple
yes, ma'am,
values.
multiple values.
That's correct. But then we say that it depends on x only. But here we have a function. So just for function whose value is not given, if it is, I'm getting you where you stop. Okay. Every single time, very rarely we are given that a is less than or equal to 0. Then we take 0 minus a, right?
Yeah.
But whenever we are given with any unknown value x or y, we never write 1 to m. We never use sigma. Then why here? This is your question, right?
Yes, ma'am.
So it is not because 2 plus x is less than a. They will also be having multiple values. What I'm trying to say that for x, there can be various values of gx. Here we are defining gx. If it is, if it would have been only x, then you don't need to write multiple lambdas. But if it is a function, then you will be having many ordered pair. It is not about x only. You will be getting many g of x because it is not x raised to power m, it is r raised to power m. So x you will be
Got
having
it.
limited from the from rn, but it is rm which you are getting because the constraint involves gx, not only x.
Hmm. Got it, ma'am.
Here we are not given anything. Such questions are only explained using the statements. So we'll leave it uh, in the form of unknown variables only. So what we are doing, we have written in the general form that this should be the case if gx is less than or equal to a. Now what we'll do, if you have to prove, come back, I need to prove what? So this is my Lagrange. What is the Lagrangian for this problem? This is it. I can't solve it further. I don't know gx, I don't know fx, I don't have x. It is just the arbitrary values which can be put in if things are given to us. But further, if I have to prove that this Lagrangian is a concave function, can you see the second part?
Yeah.
Then how will do? That Lagrangian is a concave function of the choice variable x on x. That if you substitute any value of x, then you will get the Lagrangian concave. See, you have f already concave.
Yeah.
F is already concave. But you have to now prove new function which you've got, Lx lambda. This is
Is
concave.
also concave.
This you have to prove. So we will use the properties of support theorem. I mean the conclusions that just like I asked you, if f is convex, then minus f is concave. If f is concave, minus f is convex. So use those. How? Let's say if we know that fx is concave.
Okay.
And if g is convex, then minus g is what?
Concave.
Why I'm writing here minus g? Because I can see that minus is here. So I'll prove this as concave, then whole function will be proved concave. Are you getting my point?
Oh. Ma'am, can we just write that?
Yes.
Oh.
Yeah.
Oh, is that the proof, ma'am?
Yes, this is the we are just writing because these are general proofs. We are not given any values for x and y. So this is how we can do. So we'll say that any value of lambda which can be greater than or equal to 0, you can say that if you expand it, it will be fx plus expand. This is lambda j aj minus
AJ lambda summation of or lambdas from 1 to m lambda j g j x.
right?
Yeah.
This doesn't have any x, so that means this is constant. If your x is linear, if your minus x square, the graph of minus x square is concave, right?
Yes, it is concave.
If you add any constant, will it remain concave?
It'll remain concave, but then it'll remain concave. Just
So we'll
move
say,
upward.
position shift will be there, vertex will be changed, but still the core character will remain same. So if my fx is concave and minus gx, I have proved that this is concave by the conclusion of support theorem. If I add constant term to concave function, it will always be a concave function only. Yeah.
Yeah.
So hence proved.
Oh, this was nice.
Or else,
So minus. So let's say if we have a function, we have a function, the new constraint function, which is minus x square minus y square.
minus x square.
Minus y square. So it's going to be concave. Is what we have proved here.
Yes.
Nice.
You could have used correspondence theorem also, if you want, like you could say x1 and x2, two members you have taken which belong to x. You have t which is 0 to 1. And then just say by concavity, because f is already concave, so it will follow the concavity of f. That f of tx1 plus 1 minus tx2 1 minus tx2
Yes,
is
ma'am.
greater or lesser?
For concavity, it's lesser
Oh,
than or equal to. Oh,
it is not maxima or
it's
minima
greater.
of fx, fy.
Oh, sorry, it's concave. Yes, ma'am. Sorry. It's concavity. Yes, so it's greater than or equal to the distributed form.
Yes. Now you can do it for g, that for each j value, your convexity of gj is what? It will give you gj, again same linear combination.
Plus 1 minus tx2 greater than or equal to
Lesser than,
g.
no, convexity.
Convexity, yes, lesser than or
Okay,
equal to.
x1 plus 1 minus t gj x2. Now, because your
What
Lagrange
is
is
minus gj?
minus, because your Lagrange is minus gj, this you have to prove. So what you will do? You
Do
need
we
minus
multiply
gj.
it?
Left, right, multiply by minus.
Minus, yeah.
So it will change the sign of inequality, right?
Thus, minus gj becomes a concave function.
Excellent. So if you add, because this is now concave, and if you add it to any constants, this one, additional constant was what? This one, aj lambda j. If you
Hmm.
add these two, these constants, still it will be concave only. So this is how, right? Did you get it?
Got it. Yes, ma'am. This is easy, relatively. But then the thing is, the initial, if the
Your voice is
sum
breaking.
is understood, then this is fine.
Come up again. Your
Oh,
voice was
is it
breaking.
better, ma'am?
Yeah, now.
Is it better now?
Yes.
Oh, the sum, it looks very complicated, but then when told how to solve, it seems doable. But then
Yeah. So
knowing only how to approach is very difficult, ma'am.
I'm getting you. There are varieties of questions, and every single question paper is having different question. You see, um, it is not that.
Yeah.
So the only thing which can help there is to elaborate, like the standard definition which you can use. For example, Lagrangian keyword was given here, so you could have used explain this, and from the constraint try to put in. This is the common thing. I mean, which we have been following everywhere.
Yes,
Apart from
ma'am.
that, you could not figure
Every
out.
sum we expanded first and
Again,
then,
it's breaking, again breaking.
yeah.
Am I audible?
Sorry, ma'am, it's raining very heavily. Sorry.
No problem, no problem. It's just, I'm hoping when you are
Is
watching
it better
videos,
now?
the recordings, for all of them
Yes,
blurred.
yes.
Were all of them blurred?
Yes, ma'am. Last 5 classes, it's blurred.
Okay, that's strange.
Yes, ma'am.
Read this question.
So, blur, ठीक है, the blur is not a problem. So, what I do is this is not going to help, ma'am. So the thing is, ये questions blurry में this that is also blurry, but then that is visible. So I open the question paper set and match the questions and do.
Okay. Okay.
Okay. Let f be a function defined. Hello.
I can hear you now. Hello? Hello?
Just 1 second, ma'am. It's the internet. Ma'am, am I audible?
Yes.
Okay.
So this question,
Okay. Ma'am, I'll read it out. Let f be a function defined on a convex set U
hmm,
in in
Rm,
in, in Rn, real number with a
number of,
cardinality n.
yes.
In lecture, we have shown that f is quasi-concave function of U. If and only if xy is belongs to the open convex set U, and t, which is an interval, lies between 0 and 1. State oh state the corresponding theorem. Okay, ma'am, this is us to prove the this is to prove the quasi-concavity.
So what is given to us?
Ma'am, they have given us quasi-concave function, quasi-concave
And
condition.
condition also. So F is quasi-concave already. If F is
Yeah.
quasi-concave, they are saying that this is the condition. Now you have to state the condition for a function if it would be quasi-convex and prove it. So this is the hint which you've got, that quasi-concave function has this greater than minima, greater than or equal to minima. So I'll write the corresponding theorem. Tell me, how will you write it? The whole thing you can copy and simply put in maxima of fx, fy, right?
Ma'am, sorry, ma'am. Could you come again?
I'm saying that you have f, a convex set. It's
Yeah.
fluctuating.
So concave set, no, ma'am. Quasi-concave. F is a yes, convex set. Yes, it's a
And then,
function. Finding convex set.
yes, let me insert one another. Now it will work. Okay. See, f is a function because it starts from convex set, right? So that is the condition which is given. F is quasi-concave, so this is the condition. Same corresponding theorem I have to write for quasi-convex. So from where I'll start? I'll start
Ma'am,
with the
so
same
again,
statement.
let f be a function defined on a convex set U in Rn,
Correct.
such that if okay, now we need to prove, ma'am. Now we need the
Yes.
proof.
Such that the last line will be f tx plus 1 minus ty.
Plus 1 minus ty less than or equal to max of fx and fy.
Now let's say if you are not getting and you don't remember the proof exactly. So you could do one thing, that prove it in the form of plotting a graph and stating that, see, this point is lying here and it is the lesser than, and give the counter example, just like I gave you for what? Fx modulus x. Do you remember?
Yeah. Yes, ma'am, you did.
We took a few values and we proved it. So if you don't remember, then you can explain it using goes that if any value the function takes between any 2 points and it is not exceeding the maximum or the bigger value, then that is the condition of quasi-convex, and you can use any 2 points, let's say x minus 2 and y. You can do x1, x2 also. If you are using y, then it's fine, or x1, x2 can also be used. So f minus 2 is what?
Ma'am, f minus 2 is 2,
F3 is,
3,
and you can take t from any
0
interval
and
0 to
1,
1. You
1.
can take anything 1, 0.4, 0.2, anything.
Yes, ma'am.
And then you find out another function,
Let's get it. We find z,
substitute the values.
the
X
value
is
is
minus
0.4 to yes, to we find the value of z, then we find the value of fz through modulus.
yes, and that will come out
It's
as
gonna be
lesser than
1, ma'am. So the
maximum of,
maximum of so it is minus 2, 2, 3 and 3. And
here
the
you here you write fx and fy, right?
oh yes, in this case we write we have two ordered pairs of which we write the maximum of 2 comma 3 is 3,
Yes,
and
which
it
is,
is less than the maximum of 3,
so we'll
then
say
thus it is
quasi-convex, right?
quasi-convex. Yes.
Now, if I have to use statements and everything to use it to prove it, then what I'll do?
Ma'am,
Uh,
so we have taken a note. So we have to f has to be differential function. It should be the convex. It should be from the convex set U.
mhm, right. You can also say, do you remember? Because any function, you just start with the definition that by definition, a function has to be quasi-convex only if all of its set, all the members which it is having has lower level sets, like lower contour, right?
Lower contour. Yes, ma'am.
So you will say any particular set which has Z, which will belong to U. For that, if you substitute function into the function, that should have what? A maximum value, and that function will always come lesser than A, right? Because it is lower level set, lower contour.
Yes.
This definition I have transformed into some, set builder form. Now, you take any points, you can consider this A, and you can have various values like fx and fy, different values, fz. For every particular value, it will be lesser than A.
Yeah.
But these fx, fy, they all are the part of SA, right?
Yes, ma'am.
These two are the part of this set. And if these 2 points are lying in between them, these 2 points have the combination as if for them, if I substitute the value here, it will always be in SA. This is also have been taken from the set.
Hmm.
And if it is in SA and SA is defined as less than A, so this value will also be less than or equal to A.
Yeah.
That means the linear combination is the least and it is lesser than the particular value. So I can I can set the analogy that ftx 1 minus ty, if I'm substituting function here, then this will also take the shape of function maximum of fx, fy.
That's quasi-convex.
See, this is fx, fy. So quasi-convex. I mean, you are simply, you are using various forms. You started with the definition of convex concave, and then you dived in to that thing, valley or linear combination of the function. Whichever way, just prove it. And you have to prove it in the same manner. For example, if quasi-concave definition is given using the linear combination, using minima, then write it, do it for convex, quasi-convex using maxima. If there would have been some other form, not the linear combination, but the hill or valley form, then counter it with the same. Are you getting my point?
Got it.